Hi, I'm Matt Delansky,
And my name's Kunal Bhakta.
and this is our SU1 Design Build project. So we are Core Mills Incorporated, and we're designing a wind turbine in order to reduce the emissions of Howlett Industries by creating a simple, minimalist, and efficient turbine. So to start, we had to design the blades, and the main focus of our blades was to make them aerodynamic to reduce drag, give them an airfoil cross-section based on wind turbine blades that already exist, and make the width tapered so that the drag is reduced, like I said. So before we first constructed the blades, we noticed that the test fan diameter was only 6.5 inches. So we decided to reduce the length of our blades from 5 inches to about 4 inches. And then through more iterations, we found we had to reduce the angle of attack to be flatter so that as it spun faster, it reduced drag. And then we also needed to seal the tips of the wings to reduce the surface area.
The second part of our turbine is the tower. During the first phase of construction, our tower's interior clearance did not meet the 4x4 requirement, so the next design had to be constructed to a slightly larger scale to accommodate. The first structure also did not meet the force requirement of 8 pounds, and the peak load for the tower was 7.779 pounds. That being said, the second change that was made was the addition of 2 lateral beams in the last section of the tower nearest to the top, as seen on the figure to the right. These were mainly added for additional support against the wind loads expected to be applied.
For the aesthetics of the tower, we wanted to create a minimal appearance that was a little bit like advanced looking. And so the main feature that we'd like to highlight is the hidden joint between the first and second section, between the vertical beams and the horizontal beams. It was kind of glued on the side, which makes it stronger. And it also makes it more seamless a seamless transition between those two sections. And then for the blades, they resemble airplane wings because they have like that airfoil cross section and they taper, and they also are connected to the hub at a leading edge. So it looks a little bit more advanced. And then on top of that, the whole tower gets tapered as it goes up, and the base has little angled support, so it kind of looks like a rocket ship. And at the very top, there's like an asymmetric design with the angled supports. And then for testing of the structure, the tower was tested by pulling a lateral load from the very top 4x4 section when the tower was held down. And this measured out the displacement as well as the force of the tower until it failed. And then for the blades, they're placed 3 feet away from a fan. And this fan was turned on to the lowest setting, and then the blades would spin and a voltmeter would track the reading. So if the voltage was higher, we knew that we made better blades essentially.
As for performance, the first tower was assumed to fail at 4.3 pounds and had a voltage of 0.2 volts for the blades. The actual load it failed at was 7.779 pounds and it had a voltage of 0.385. For the final tower, we assumed the peak load would be 9.8 pounds and have a voltage of 0.4 pounds for the blades. The actual load supported was 12.968 and it had a voltage of 0.478 volts. The performance index for the blades increased from 4.299 to 6.512, and the tower performance index changed from 17.15 to 18.30.
And as you can see in the force versus displacement graph in the top right, the second tower is much stiffer because at the same displacement at around 2 inches, it can hold almost twice the force of tower 1, meaning that our improvements made it much stronger and also held a much higher peak load. And then to analyze the structure, we first should go into how it failed. And you can see in the little red dot on the right in the picture that is where the structure failed because the column buckled, and it buckled because the lateral force pulling it created a bending stress in that column, and the angled beam coming out at it gave it a point stress in the same direction, causing more bending stress, which made it fail. And then this being said, our tower was still relatively strong and it had certain design intent because there was a lot of redundancy. There was 4 different ways that the load could be transferred. So if a single one was broken, it would be transferred to the other 2 because there were 2 spots where all of the loads connected at the joints. And the joints were also the most important part. So we made them a lot stronger because they failed there at the first tower. So we wanted to make sure that the tower failed at a column or something else the second time.
The biggest problem our team had was the design of the structure. To solve this problem, our team collaborated and put in research towards the best designs possible. In doing so, we were able to meet the requirements given. During this project, we learned many important skills that would be used during the rest of our time at UCSD and future careers, such as the engineering design process.
And these are our acknowledgements. Thank you.
Thank you.